to our lecture, which I've titled Our Fragile Earth. This is Geography 1200, Human Geography. I'm Jim Fonseca, and I know that this is a human geography class, but I wanted to present this lecture on it. So this is about, in the context of human geography, while we're going to lop over a bit into physical geography as well. The idea is, let's look at this Earth as our home of the 7 billion people, now going to be perhaps 11 billion, they're saying, by 2100 or so. So let's look at the Earth as our home. And an interesting thing about the Earth, and I have a globe here, a 16-inch globe, which is important because we're going to do a little math later. The Earth is actually an oblate ellipsoid. It's a fancy name. It simply means that it's a little bit flattened at the poles and a little bit fatter at the equator, which makes perfect sense because as the Earth spins around, centrifugal force kind of pushes some of the Earth's material and water and so on. So it's a little bit fatter around the equator. Not much, only about a 25-mile difference or so. So if somebody says, well, how big is the Earth? The Earth has a circumference of 24,900 miles. So let's call it 25,000. To give you an idea of what that is, so 25,000, if you could drive 1,000 miles a day, that's a lot of traveling. Some of you may have driven 1,000 miles. It would take you 25 days to drive by car. Now the diameter of the Earth, so now again, the circumference means measuring the Earth all the way around, like with a belt basically. Whereas the diameter means going through the center of the Earth. Now that's a shorter distance. About 7,900 miles is about 8,000 miles. And if you were to go directly through the center of the Earth, a better analogy than driving is to think of an elevator. Turns out fastest new elevators go about 22 miles an hour. So if you traveled 10 hours a day in the elevator, you would go 220 miles each day, and it would take you about 36 days to go from the North Pole to the South Pole. I apologize, there's an error on the slide that says hours, but believe me, it's days. By the way, bring sandwiches, there are no rest stops. So that gives you some idea of the basic dimensions of the Earth. And a phrase we're going to look at now, or a word, is called the antipode. The antipode means, given any point on the Earth, like say Australia, what is the exact opposite point if you went through the center of the Earth? And I don't know if kids still say this. I know when we were kids, people said, well, if you dug a hole all the way through, you'd end up in China. Well, it's not true at all, turns out. Like a lot of things aren't true. This is a map. It's a little bit hard to see at first. You see my cursor moving around. So what you see in kind of purple is the normal map of the Earth. Here's North America, here's Africa, and so on. And what you see superimposed on it in white is exactly what's on the opposite of the Earth. So it turns out, for example, that there's really nothing in the United States. I shouldn't say nothing, but there's no landmass opposite us, because here is North America on the other side of the Earth, and upside down, here's the United States. We would be in the South Indian Ocean, which coincidentally, this is that area where they believe that Malaysian airplane disappeared, extremely rough seas and so forth, so they haven't been able to find it. And off of the east coast of the United States, if somebody drilled a hole there to the opposite side of the Earth, they would come out at Australia. In fact, since only about a third of the Earth is land, it turns out that very few places have anything opposite them. So, for example, here's Chile and Argentina. It turns out they're the ones who would dig down and come out somewhere near China if they could dig all the way through the ocean. Here's New Zealand, is on the exact opposite side of the world from Spain and Portugal. So the point is, since only about a third of the earth is land, very few places have these antipodes. But it's just, every place is an antipode. Very few places have land intersecting with other land on the other side of the earth, because only about a third of the earth is land anyway. And while we're looking at the earth, there's a map you may see. This is called a Mercator projection. It was one of the first kinds of maps made. And it, just a caution about these maps, it very much distorts the size of the earth, which is partly why we don't use these maps very much anymore. Because what it's doing is, the way the map projection is made, it's fairly accurate around the equator, which is here, and it's accurate for distance and direction, but they distort shape. And we'll explain that in a little more detail, but just to show you the distortion, take a look at Greenland. See the cursor moving there up near Canada, and compare it to South America. Okay, doesn't it look like Greenland is bigger than South America? Not true. Here's a map that accurately, or more correctly, displays size, and you see that actually Greenland is about 1/8 the size of South America. And if this works, we'll go back, take a look at it one more time to see that distortion in size. Greenland much more appears much larger than South America, whereas that's totally false. South America is much larger than Greenland. And you may ask, well, why make an inaccurate map? Well, all flat maps are inaccurate. You can't take a curved, imagine you said, well, I want to put this surface of the globe in a book, right? So you peel the paper off the globe, right? You can imagine what happens when you take that curved paper now and you crunch it all down to try and fit it in a book. Something's got to give. Only a globe can correctly show size, distance, and direction, all correct, because you can't transfer that curved piece of paper from a globe onto a flat map without crushing it. So all flat maps have to distort something. So they might distort size in order to keep distance and direction accurate, as the Mercator projection does, or other kinds of maps may distort distance and direction and show size correctly, or they might distort size and distance but show direction correctly. So the secret of making what looks like an accurate map is to put all that distortion in the ocean, right? Since the earth is about 31%, I think it is, land. I think it's 27% land. Most flat maps then try to put that distortion in the ocean where people don't notice it. They don't say, well, wait a minute, you don't really know how big the Pacific Ocean is unless you're trying to measure it or something on the globe. So map distortion. Another interesting thing about maps is, we get used to the idea, all the maps I've shown you so far have north at the top. We get used to that idea and we think that, well, that's accurate. Somehow if you have some other kind of map, it's inaccurate. Not true. I mean, in outer space, there's no up or down. You could look at if you're an alien coming from another planet, you might be coming from the bottom up or the right side in, or who knows. There is no up or down in the universe. It's just like, well, this is the standard way we show it, so we get used to it. And in fact, you could make it an accurate map. This particular one is called there's several of these you can look at on the web. The Australians' view of the world, or Australia's view of the world, and you see, well, this is what, the joke is, this is what you guys look like from down under, because in fact, the very terminology, Australia calls itself down under. or I guess other nations have called it down under. They probably call themselves on the top or something. But anyway, it's just a cute map to show how you can have an accurate map, accurate to the extent that a flat map can be accurate, and have Australia on the top of the map instead of the bottom. Another interesting thing is what are called great circle routes. What it means is it's because of the distortion you get on flat maps, or even if you look too quickly at a globe, it's sometimes kind of mind-boggling the actual directions you fly in. Now, even though we're looking at a globe, and I've practiced a little bit, hopefully you'll be able to see this. But if you were going to fly from, as this map shows, New York to Japan, and you just look quickly at a globe, you'd say, well, okay, we're going to leave New York, fly west across the United States, then we'll get to the Pacific, we'll go near Hawaii, we'll come around, we'll end up near Japan, and most of that flight after we leave the United States is going to be over the Pacific Ocean. Not true, because, and if I can show this to you and hold it properly, actually what you do is you put to see where you're going to fly somewhere, you put a string on a globe. So I've got one end of this is in New York, the red band. The other end of it, if you can see it, is in Japan. And you see that as we show on the map, on the PowerPoint projection, most of that flight is overland. First of all, you leave New York and head into Canada. You go kind of up and over Canada, over northern Alaska. Then you come down on the eastern side of Russia and then into Japan. So actually much of that flight is overland, and you really don't get much time over the Pacific Ocean at all. But that's the kind of the deception you get out of flat maps. In these, again, this route, when you transfer the line on a globe, a straight line on a globe, onto a flat map like that, it's called a great circle route, because they usually end up being like a circle. Another interesting thing, when you look at the globe as this home of the humans on the earth, some other interesting things about distance and direction and so forth. And this is something that's really coming into the news right now. For centuries, ships traveling between China and Europe, a lot of trade going back and forth. We got to keep all the Walmarts in Europe stocked up with stuff from China. And traditionally what happens is the shortest route, the traditional route, is that you leave China. I find my cursor here, there it is. And you go around Southeast Asia, you go south of India, you go over between Africa and Saudi Arabia, up to Red Sea, through the Suez Canal, which they're widening, by the way. You come through the Mediterranean, go around Spain and Portugal, come to Europe. That's the way all the shipping goes now. Of course, if you go to the United States, you go across the Pacific. But anyway, because of melting sea ice in the northern Arctic, due to changing climate and so on, actually what's happening now is it's a shorter distance in summer when much of that ice is melted, and they help it along with icebreakers, is for ships to leave China. There's the cursor. Come up here between Korea and Japan, go around Russia, come up between Russia and Alaska at the Bering Strait, cross the Arctic Ocean here, and it's called the Northern Sea Route, and then you can come to Europe and come in either to the Russian port of Murmansk here, or you can come down all the way to Europe, back to Rotterdam again, and this is shorter. And when I say literally, this is happening, kind of as I speak, because one ship tried this route like 4 or 5 years ago. 2 years ago, 5 ships tried it. this last year, about 20 ships tried it. So more and more we're going to see this route as a new maritime route to be shipping goods from Eastern Asia to Europe. Second interesting thing about the globe is back in the days of the Cold War, and in fact this map still shows it as the Soviet Union. People were worried about missiles. The United States and Soviet Union had missiles pointed at each other and so on. Everybody thought, well, we should be watching because here's Moscow over here, right, under my hand, and here we are. So we're going to watch along the East Coast for these missiles to come in. Not true. Again, the shortest distance between the Soviet Union and North America, if you can see that, is across the pole. And in fact, the United States and Canada set up during the days of the Cold War. You can see the arrows coming in there. What was called the DEW line, DEW. It stood for Distant Early Warning Line. We had a string of radar stations across the Canadian and Alaskan Arctic that watch for missiles with radar and all that. That was like in the 50s they built that. There were about 40 or so stations all the way across. Now they've disbanded those because now with high altitude airplanes and satellites and so forth, you don't need a ground radar station anymore. But again, the point of this is to illustrate that the shortest distance between 2 points is a curved line on a globe, and missiles from the Soviet Union, if anybody ever shot any off, would come right over, and so do air flights, by the way, airline flights. If you fly from like New York to Moscow, that's kind of the route you take, and they limit because of the accumulation of solar radiation at the poles, which is what gives us, you've heard of the aurora borealis or northern lights, that it's radiation from the sun that flickers around the poles because the magnetism of the North and South Pole attracts that radiation. If you're an airline pilot, you're limited in the number of days that you can fly a plane per year because that radiation does have an impact on your health. So if you're just a passenger and you fly once a year, it doesn't matter. It's like getting an X-ray at a dentist or something. If you're a pilot, they will not let you fly that route every day for months at a time. A little bit about hemispheres. Again, looking at the globe as a whole, hemispheres means half. Some of you into cars may know there's a hemi engine. It's a hemispherical or half a spherical engine. And a lot of terms. For example, you've heard the eastern and western hemispheres, and that divides the earth. Eastern and western hemispheres divides the earth the way this metal bar is here from the poles. And some lines, line is a 0 degree longitude line. So these lines are called longitude lines. And 0 degrees is in Greenwich, England, simply because the British kind of standardized the system, and they said, well, they had an astronomical observatory in Greenwich, England, which is like a suburb of London now. They said, well, we'll call it the 0 degree line. And that's the convention. That's the standard way we still use that number. Is Greenwich, England is 0. The exact opposite of the Earth is 180 degrees, which is the international date line. It happens to run through the Pacific. Kind of lucky in a way that it is in the Pacific, because the international date line is where, somebody, as the Earth rotates, right, the East Coast gets sunlight first in the United States, and then 4 hours later or whatever, California gets sunlight when the sun rises. Somewhere you've got to say somebody's, it's Monday everywhere, right? Well, it can't be Monday everywhere, because who's going to get to Tuesday first, right? So at some point, so when the sun rises on the international date line, that's where we say on one side of it it's Monday, on the other side it's Tuesday. simply because somewhere on the Earth we have to break, somebody's going to say, well, it's Tuesday now, somewhere. And I say it's fortunate it's in the Pacific, so you don't have a country like Australia or something divided in half, where like half the people, this of course happens with time clocks as well. Those two hemispheres, the eastern and western hemispheres, are also known as the Oriental and Occidental. We hear the term Oriental much more than Occidental, but that's the opposite of it. Orient means east, so Oriental means eastern. And nowadays, of course, the term is also used for like food. You say, well, they have Oriental or Asian cuisine. It's not really proper to use the term for people to say, well, he's Oriental. Nowadays, we say he's Asian. She's Asian, whereas it's still proper to use the term for food. Occidental means Western Hemisphere, and again, it's not. The northern and southern hemispheres are defined by the equator, which is 0 degrees. The poles are defined as 90 degrees. And of course, the equator is it's the middle of the Earth in the sense of how the Earth rotates, defined as that. The middle of the Earth on the day when it gets the most direct sunlight at noon, on the days when all of the Earth gets exactly 12 hours of daylight, 12 hours of nighttime, called equinox, or 12 hours of daylight and 12 hours of sunset time. So we have the eastern and western hemispheres, defined by longitude. The northern and southern hemisphere is defined by latitude. And not spending too much time on those because I know you're familiar with them. But I wanted to talk a little bit more about the land and water hemispheres. Back to the thing about the Earth is 70% water and only 30% land. And an interesting way to see that. By the way, I encourage you, go find a globe. Maybe you have one buried in the attic that your parents gave you when you were 12 or something. Pretty much any library has a globe. But just go there at some point and kind of play around with it and look at these things. If you center the Earth, so what is the water hemisphere? And I practiced this a little bit. So hopefully this comes out more or less what I want to show you. Basically, the water hemispheres, you can position the globe in such a way that when you look at half the globe, you pretty much only see water, and hopefully that's what you're seeing. Now, obviously, you're on the Pacific Ocean, focused on the Pacific Ocean. And if you then go to the opposite of that, right, the antipode, right, so go to the opposite side. So that was the water hemisphere. If you now focus the Earth more or less on Africa and Eurasia, around where Saudi Arabia is, because Saudi Arabia is where Africa meets, the Middle East and so forth is about where Africa meets Asia. And actually, Eurasia is the term for Europe and Asia as one unit, because really Europe is a pretty small piece of property compared to the Earth as a whole. So that's referred to as the land hemisphere. And hopefully I showed you that more or less correctly. So, and those are kind of colloquial or vernacular terms, but the point of that is to make the point that the Earth is about 70% water and only 30% land. Now, we're going to talk a little bit about the dimensions of mountains and so on the Earth. How rough is the topography? Because leading up to talk to I think give you some surprising information about the biosphere where people and all of life lives. So I look at this globe. This is from actually in Ohio University Zanesville globe. And you feel these mountains, you know. I know you can't see this because I tested it, but you see these mountains here. Here are the Himalayas, the highest chain in the world here, basically between India and China, the plateau of Tibet and so forth. Well, how tall are these mountains really? Because usually these good quality globes will tell you, well, the vertical exaggeration of 10 times or 50 times or whatever. So when you think about it, let's talk about what is the tallest mountain. By the way, this is kind of a trick question. Sometimes in a live class I say, well, what's the tallest mountain? Actually, it turns out the tallest mountain is on Mars. And it would be about 10 miles high by Earth standards. But anyway, we're talking about on Earth. And it turns out it is true that Mount Everest is the highest mountain. It's a little more than 29,000 feet. Because we traditionally measure it by sea level. Now and that's kind of the standard definition. Now it turns out there's a mountain in Ecuador, Mount Chimborazo, which is by sea level elevation quite shorter than Everest. It's about 20,500 feet. Mount Chimborazo in Ecuador. In fact, I'm going to show you. I found a map of where that is. You see it right there in the center of Ecuador. And down here in the bottom right, you see where Ecuador is. This is South America, which, by the way, is on the equator. And in fact, Ecuador is a Spanish word for equator. So that's an easy one to remember. The equator runs right through it. And remember the thing about the Earth is fatter around the equator because it's an oblated ellipsoid and it's a little bit shorter going through the poles, and it's a little bit fat around the Earth, and it's about 26 miles difference, which isn't a lot compared to the 8,000 miles. However, this Mount Chimborazo in Ecuador could be defined as the tall. Think of it this way: it's the tallest mountain in the sense that it's the point that sticks out most from the Earth, as a physicist might measure. They said, well, the tallest mountain is the point, define the center of the Earth, what's the farthest point out from it? Because the Earth bulges out in this direction. No way of thinking of it, this is as the moon revolves around the Earth, this point is the closest to the moon. Think of it that way. But again, that's not the standard definition, is by sea level. Another example is actually Mauna Kea, an island in Hawaii, and actually any of the Hawaiian islands are actually taller than Mount Everest, in the sense that if somebody pulled the plug on the Pacific Ocean, this diagram illustrates that Mauna Kea, which is one of the Hawaiian islands, is 33,400 and some feet above the floor of the Pacific Ocean, which would actually be taller than Mount Everest. However, our convention is that we measure the height of mountains from sea level. And if you look at this island in the Hawaii, you see that it's less than 14,000 feet above sea level, even though 18,000 feet is hidden below the ocean. And so there's three different ways of looking at heights of mountains. How about depth? The deepest ocean trench is the Marianas Trench. It's in the Pacific, and it's located a few thousand miles southwest of Hawaii. Think of it as it's kind of around between Hawaii and New Zealand, down in that part of the Pacific Ocean. 36,000 feet deep. So actually, if somehow you could pluck the top of Mount Everest above sea level 29,000 feet, drop it into the Marianas Trench, it would disappear, because the trench is deeper than Mount Everest is high. Now, what this is leading up to is this, though, to talk about going back to where we started with the when I was showing you that the mountains stick out on that 16-inch globe. An elevation is called relief, is another term for it. So even if, and so Everest is like 6 or 7 miles, 6 or so miles tall, and the Marianas Trench is 7 or so miles deep. So even so, you know, how does that feel accurately on a globe? So you get 8 miles. Let's call it 8 miles, even though that's taller than Everest and Mauna Kea and so on, and it's deeper than Marianas Trench. Let's just say 8 miles. Remember, the Earth's thickness is about 8,000 miles. So you've got 8 miles of relief or elevation compared to the 8,000 mile depth of the Earth. Remember, 36 hours on an elevator to get from the North Pole to the South Pole. So here's the math. That's 8/8,000th, we'll call it, to make it simple. So that means 1/1000th of an inch is the actual relief. So if you were trying to make an accurate globe, it turns out that the tallest mountains like Everest and the deepest ocean trenches like the Marianas Trenches would be about the thickness of a piece of thick paper or cardboard. And I actually looked this up and did the math and so on. And there's the places you can see this. 1 or 1600ths of an inch, 0.016. And it turns out that's about the thickness. When I say thick paper or thin cardboard, you know those cards that you find in magazines? It's about that thickness. So I have a visual aid here. So if I wanted to put Mount Everest in its proper thickness on the globe, I would take a thickness of piece of that cardboard and stick it on here, and that's the actual thickness. And what would be the point of doing it? I mean, you know, I mean, you would still hardly be able to feel it, but that's the accurate amount of the relief on a 16-inch globe. It's a very tiny amount, and you can hardly feel it. And we'll come back to that one more time. Now, I want to talk a little bit about the 4 spheres of the Earth. We have the lithosphere, which means land or rock. In fact, lithos was the Greek word for rock. The atmosphere, of course, you know, means the air. Hydrosphere refers to the water, meaning all water, seawater, freshwater, lakes, and so forth. And the biosphere means all the life on the world, whether it's birds in the air, worms in the ground, people, fish in the sea. So you get some animals kind of in the atmosphere, some in the hydrosphere, some in the lithosphere. And all of that makes up the biosphere. And just an interesting thought. Next time you're at the seashore, you go to Myrtle Beach or something. At the shore, all 4 of these spheres intersect and interact. People say, well, define the seashore. Well, the seashore is where land meets the water. Yeah, but it's also the only place where those two interact with the atmosphere as well. And of course, the atmosphere, the air is out there making the waves and giving you the salt spray at the beach and so forth. And meanwhile, you also have seagulls and fish and so on. So you've got the biosphere interacting there as well. So the seashore is land, water, atmosphere, and the biosphere all fitting in together. The amount of water on the Earth is tiny. So back to the analogy of the globe. And so if the deepest ocean is only as thick on this globe as a piece of that very thin cardboard, how much water can it hold? And you see, if on this picture, on the PowerPoint that if you consolidated all the water into a ball, it looks about the size of a ping pong ball or so, and stuck it on over North America. That's how much water there is. So it's not the case like if this globe accurately portrayed the, you might think, well, my fingertips would sink into the Pacific. No, they wouldn't. All you'd have is the impression, well, it's wet. I mean, that is how much water is on the globe, fresh and salt water. And same is true with air. In fact, this diagram shows the water. This time it's centered over Europe. And here's the air, also centered around Europe. Looks like a pinky, those pink balls that kids have. And you may say, and you'd be right, well, wait a minute, but there's air way up here and so on in outer space, and there's little molecules of air up, like where airplanes fly and so on, which is probably around maybe where my cursor is going. True, but it's very, very thin. Those are scattered molecules. You know the thing that as you climb up a mountain, the air gets thinner and thinner. There's some real life impacts of that. I mean, people, you have to wear oxygen masks, like if you climb Everest. If you remember, Denver's the mile high city. They have to adapt their recipes. They have to cook things a little bit longer than you do at sea level. Smokers, their cigarettes go out because there's not enough oxygen. They go mountain climbing or whatever. So this is the size of the amount of air. So the point of saying all that is, okay, if you reduce the air to sea level pressure, this is how much air there is at sea level pressure when you bring in all those thin scattered molecules that are all up in the upper atmosphere and bring it down to Earth, kind of pressurize it, so to speak, to make it the same density that we normally live in, pretty much around sea level and so on. So this has, remember I titled this talk, Our Fragile Earth, and one of my points is when you hear about pollution, sometimes you say, oh, the world's so big, but remember, and we'll see this even more so in a second, we're going to see about fresh water, but when your neighbor changes his oil and dumps it down a creek in the woods or something, say something, because there's not an awful lot of room here to absorb all this pollution and stuff that we dump into the water and that we dump into the air. And it just gives you a different perspective on it. Now here's the thing about fresh water. So we know, back in that last picture you saw that that all the water on the Earth is like about the size of a ping pong ball on that size Earth, that size globe. Well, when you start talking about fresh water, well, first of all, it turns out 97% of the water is salt. So 3% is fresh water. And of that fresh water, let me go through this once and I'll go back over it. Most of it is frozen. It's in ice caps. 69% is in ice caps, Antarctic ice sheet, glaciers. And 30% is in the ground. It's groundwater. Because, of course, as you know, it rains and the water seeps all the way down to the bedrock and so forth. Only 1% of the 3% that's fresh, really only 1% is in lakes and rivers, and even some of it is in the atmosphere, about 1/10 of 1% at any given time, in clouds and so on, waiting to fall back out again as rain. So only 3% is fresh, and a very tiny amount of that, in fact, only 1% of the 3%. I'm not saying 1% is in lakes and rivers. We're saying 1% of 3% is in lakes and rivers. So it's a tiny amount. And of the ice, you see at the bottom of the PowerPoint, the amount of water is very unevenly distributed in terms of ice. 90% of it is in Antarctica. 9% is in Greenland. So there's like 99% of it is right there. So the 1% left is frozen somewhere, like maybe in northern Alaska, northern Canada, a little bit in high mountains all over the world. I mean, you can have an ice cap. If you get a very tall mountain, like above 20,000 feet, even near the equator, you'll get ice caps because it's cold enough up there. But again, that's a small percent of ice in the world. So again, the amount of fresh water is very limited. The amount of fresh water in lakes and rivers is particularly limited because the vast majority of the fresh water is frozen up in ice. And our last sphere we're going to talk about today is the biosphere. Where all of life lives is a very thin, tiny layer. Because when you think of how vast the Earth is, and all this stuff about 8,000 miles, right? So if you're looking for life, let's start with the Earth and the lithosphere. And you start digging down, you know. If you dig a hole, have you ever watched them like dig a hole for a basement or a big office building or something, they go down? You know what's down there? There's nothing down there. The vast majority of life in the soil is pretty much in the upper 100, maybe 200 feet. You know how deep do tree roots go down? You see trees blown over by the wind. You know, and that's where it's in that upper layer, that upper 100, 200 foot layer of soil. That's pretty much where all the earthworms are, all the chipmunks are, all the snakes, lizards, beetles, whatever's down there. All the plant life, the fungi and the mushrooms and so on, are all in that upper layer. They're not down 20,000 feet. I mean, yes, it turns out there's bacteria. They even find bacteria. They can find bacteria in like deep oil wells, and they drill down 10,000 feet or something. There's bacteria down there. But that's not where the real life is that we're talking about, you know. And people, of course, we live with our feet on the ground. So we're not, you know, unless you're own a house that's built underground or something, you know, we're pretty much all on the surface of the Earth. And the same here too, you say, well, yeah, but the land goes up to 20,000 feet. Well, again, though, the question, what's up there? Remember the comment about you get over 20,000 feet, you have an ice cap. You get over 10,000 feet, you pass the tree line. It's too cold, generally, at most latitudes for trees to grow beyond 10,000 feet. So my point is, it's a very thin layer. And even when you go up 10,000 feet, it's not like you have life 10,000 feet thick. It's only following the soil. The life is pretty much in the soil. So the trees and everything, you're only talking about a thickness of a few hundred feet going up the side of the mountain and so on, where much of that life is located. So mountaintop life is very sparse. You have little mosses and lichens and fungi and things that are up, you know, beyond the tree line. You know, how much life is in the atmosphere? Well, you get birds. I mean, look out the window now. How many birds do you see? It's not like, you know, it's wall-to-wall birds in the air. You know, yeah, birds fly up, I don't know, I suppose hawks and things fly up a couple hundred feet, and eagles. But most of them are just, you know, just at the height of the trees. And the same thing is true with the oceans. You're going to think, well, you know, the oceans are 5 or 6 miles deep in some places. Mostly they're pretty shallow, less than a mile and so on. But, well, it turns out the life in the ocean is very constrained too. The vast majority of life in the ocean is in 600 feet because that's the maximum depth that light can penetrate. If you know anybody who does deep sea diving or something, they go down in these suits. Once you get below 600 feet, it's pitch black. You look up at the sun, it's still pitch black because light cannot penetrate more than 600 feet into the ocean. That's where, because light is there, that's where the plankton and algae are, you know, little tiny fish and microorganisms that feed on the plankton and algae and the small fish and the big fish and everything. And yes, turns out whales can go down several thousand feet. They go after squid that go down. But again, that's very, very rare. It's almost like the reverse analogy of, yeah, there's an eagle way, way up, but how many of them are there? Most of the time, whales are in the upper 600 feet, feeding on the other fish that live in the upper 600 feet. 600 feet, by the way, so you get this zone, pretty much maximum 600 feet. It's approximately the height of a 40-story building, or in this case, the depth of what would be a 40-story building, approximately. So the moral of the story, so to speak, is to illustrate how fragile. So now if you recall that the thickness of the highest mountain and the deepest ocean trench could be represented by this little tiny piece of thin cardboard I punched out. And then, so if that little tiny thin cardboard is the thickness of Mount Everest, but we all know life is not like 29,000 feet thick. Life is just, a few hundred feet into the soil, 100 feet up into the air where birds fly, 600 feet deep in the ocean. So where does all this life live on the earth? And the answer is, it's about, have another visual aid, it's about the thickness of a piece of plastic wrap. And this is why I called this lecture, It's a Fragile Earth.